Okay, welcome everyone. This flipped classroom video is going to focus on the topic of calorimetry. So before we start to talk about calorimetry, I have a thought question for you. A blacksmith has a piece of red hot metal that's at 1,000 Kelvin, and then he places it into a bucket of water next to him that's at room temperature. So go ahead, pause for a second, think. What will happen to the temperature of the water and the metal when he puts that hot metal into the water? Okay, so hopefully you said the temperature of the water will increase and the temperature of the metal will decrease until they both end up coming to the same temperature. So let's go ahead and talk about why that is, because that's one of the key ideas behind calorimetry. So calorimetry is a process of determining the amount of energy in a sample. So this is commonly used for things like food or for fuels to figure out how much energy they have. So in this process, we have a contraption at the side, like that picture, that is called a calorimeter. So a calorimeter is a very well insulated container. And inside that container, we have water. We usually also have a thermometer and then something to circulate the water so that it makes a nice even temperature all throughout the water. We don't get any hot spots or cold spots. And within that first container, we have an inner container, and that is where our sample is held. And we usually have some kind of way to ignite the sample in there. So we often have ignition wires. We have a spark. If we have oxygen and we have fuel, we get a flame. So as that sample burns, all of the heat from our sample is going to go from our cup into the water. And by measuring the change in the temperature of the water, we can figure out how much energy or how much heat was released by our sample when it burned. So the key idea with calorimetry is that heat flows from hot to cold. So it flows from our hot burning sample to the cold, the water surrounding it. And eventually the water and the sample will have the same temperature. This is because heat's going to continue flowing until they're the same temperature. So the key idea here is that the heat given off by a sample must be equal to the heat absorbed by the surroundings. And that allows us to come up with a really, really simple equation that the heat, or Q of water, is equal to the opposite of Q of the sample, the heat of the sample. So the reason why we have that negative sign in there, water is absorbing energy, so that's a positive value, versus our sample is giving it off, that's a negative value. So we have to have that negative sign there, so negative times a negative gives us a positive. And just one little word, calorimetry, as I mentioned, is commonly used to measure the energy in foods historically. So this is also where we get that word calorie from. So if you look on the back of your package of food, it says calorie. Now, one little known fact is that we have capital C calories and little c calories. In this case, capitalization does make a difference. So capital C calorie has become known as the kilocalorie, which is actually 1,000 little c calories. And that capital C calorie is the unit of energy that we commonly use to describe the amount of energy in food. So if you look on the back of your package of whatever you have in your pantry, you're going to see that's going to be that capital C calories. So whenever you have something that's 100 capital C calories, really it's 100,000 little c calories. We just use the bigger number because it's easier to count. Okay, so there are three main steps for solving calorimetry problems. The first one is we need to determine the heat absorbed by the water. And we're going to use that Q equals MCAT equation that we've been using so much this week. Q equals M, the mass of the sample, times C, the specific heat of our water in this case, times the change in temperature. So a few things to point out for this first step. C is going to be the specific heat of the water, so it's going to be that 4.184 joules per gram degree Celsius because we're talking about liquid water in this case. And the mass is going to be the mass of our sample. Once we know how much heat is absorbed by the water, we can figure out how much heat was released by the system or by our sample. So that's where we're going to use that Q of water is equal to the negative Q of our sample. And then finally, and sometimes we don't have to do this step, but frequently we do, we need to find the unknown factor for our metal. So maybe we're asked about the temperature of the metal, maybe we're asked about the specific heat, maybe we're asked about the mass. So we're going to find whatever the unknown is by using that Q equals MCAT equation again. So Q equals M times C times delta T. Key thing here, The specific heat, we'll talk about the specific heat of the metal that might either be given to you or a value that you're solving for. And the mass, the second time we use it, is going to be the mass of the metal, not the mass of the water. So make sure you're careful to distinguish between those two values. Okay, so let's go ahead and try an example problem. A 50-gram sample of metal is heated to 125 degrees Celsius and is placed into a calorimeter with 250 grams of water with an initial temperature of 25.3 degrees Celsius. If the final temperature of the water is 32.1 degrees Celsius, what is the specific heat of the metal? Well, step one, we need to find the heat absorbed by the water. So we're going to use that Q equals MC delta T. Okay, now I want to go ahead and plug in my values. The M initially is going to be the mass of my water, which is 250. C is going to be the specific heat of my water, that 4.184. And my delta T is final temperature of the water minus the initial temperature. So 32.1 minus 25.3. So if we go ahead and plug that all in, we end up with 7,112.8 joules. And I'm not going to worry about sig figs yet. I'm going to say that for my final step. So I'm just going to keep all of them. Now I need to find the heat released by the metal. Well, it's a pretty simple step. Basically, we go ahead, plug it in, and we take whatever value we got from step one and just put a negative sign in front of it. So we get negative 7,112.8 joules. So once we have all that, we want to find the specific heat of the metal because that's what this problem is asking for. So I'm going to take my Q equals MC delta T and rearrange my equation. So I get C is equal to Q, the heat, divided by the mass times the change in temperature. So my Q is that value I just found in step two, that negative 7,000 number. M is going to be the mass of my metal because right now I'm thinking about my metal. And then my change in temperature is going to be my final temperature of my metal minus my initial temperature of my metal. So if we think about this, be very, very careful here. The final temperature of my metal, it has to be the same as the final temperature of my water. Because when I put those two things together, eventually they're going to come to the exact same temperature. So I know that my metal is going to end up at 32.1 degrees Celsius when it started at 125. So make sure you do that. If you get to your answer, it should all work out where you end up with a positive specific heat. If you have a negative one, you did something wrong someplace. And then we want to solve our equation and round to 3 sig figs. So 1.53 joules per gram degree Celsius is the specific heat of my metal. Okay, let's go ahead and try another example. So a 35-gram sample of zinc is heated and placed into a container with 100 decimal point grams of water at 22 degrees Celsius. If the specific heat of zinc is 0.390 joules per gram degree Celsius, and the water's final temperature is 31.3 degrees Celsius, what was the initial temperature of the zinc? Okay, so this problem's a little bit different because it's asking about the initial temperature of my metal versus the last one we were finding the specific heat of my metal. But we'll get to that. So let's go ahead and do the same first step. We want to find how much heat was absorbed by the water. So we use that Q equals MCAT. And then we're just going to go ahead and plug in our values. So M is the value of water, remember? C, that 4.184. And then we have final minus initial. So that gives me a value of 543.92 joules for my heat absorbed by the water. Now I need to find out how much heat was given off by my sample. So basically I take the negative of whatever my previous answer is. So I get Q of my sample is equal to negative 543.92 joules. Okay. And then step 3, if we move on, we're going to use that Q equals MCAT equation again. Now this one gets a little bit yuckier with the algebra, but we can do this. So we have our Q equals MCAT. Now what I recommend for this one is go ahead and replace delta T with T final minus T initial. But one thing you want to be careful with, that M times C is times the difference of TF minus TI. So either you have to distribute it right away, which you could, or what I would do we're going to go ahead and solve for the TF minus TI. We're going to bring that all over to one side and then plug in our values. Okay, so if we take a second and look at this, TF minus TI is equal to Q divided by MC. So basically, I divided both sides by MC. Now I go ahead and plug in my values. So I know that the final temperature of my water and my zinc will be the same. So that's 23.3 degrees Celsius. My initial temperature of my zinc, I don't know. So I'm going to leave that just TI. My Q is from step 2. My mass is the mass of the zinc. And then I'm multiplying that times the specific heat of my zinc. Now if I go ahead and solve the right hand of my equation, I end up getting a value of negative 39.8 degrees Celsius. If I go ahead and finish up my algebra, I'm going to subtract that 23.3 degrees Celsius from both sides. That gives me a negative initial temperature is equal to negative 63.1. I go ahead and then divide both sides by negative 1 or multiply by negative 1. I get 63.1 degrees Celsius. So the algebra is a little yuckier for this one, but we can still go ahead and solve for that. So if you have any questions, please let me know. Remember, you can reach me on Remind or email or during office hours tomorrow. And then please keep in touch. And thanks for watching, everyone. Have a great day.